So as we move into section 4.4, there are some properties of logarithms that we need to be aware of. Okay, now some of these we've already kind of talked about, but we're going to expand on them a little bit more and get really comfortable with them because as you move further and further in mathematics, these are going to become a big issue. Okay, for example, in calculus, these log properties are a really big deal, and we use them as shortcuts quite a lot. Or sometimes, in fact, you might even get stuck on a problem until you remember the log property that has to be used. So they are very important as we move forward. Okay, just as a reminder really quick, we can convert between logs and exponentials. Okay, they mean the same thing, they're just different ways of expressing it. So if I have x equals a to the y, that's the same thing as saying log base a of x equals y. Remember, the whole point of a log is to get the exponent by itself. So whatever was up there in the exponent position as an exponential is what's by itself in log form. Okay? And the base of the exponent is the base of the log. So just keep that in mind as you're working with logs. We talked about these 4 properties here in the previous section. Remember that if 1 is in your argument position, that log is always equivalent to 0. Reason being, if I were to convert this to an exponential, I would have a to the 0 equals 1. You know, remember, if you raise something to the 0, you get 1. So shortcut of that, if we ever see a 1 in the argument position, we know that log is equal to 0. When you have a log where the argument and the base are the same thing, that equals 1. So if I were to convert this log to an exponential, I'd have the base of a raised to the first power equals this argument of a. And that is a true statement, so that's why we know when your base and your argument are the same, that log is equal to 1. Here's a log that's got an exponent in it. So if I were to convert that to an exponential, I would start with the base. That base down there is a. A to the x would have to equal the argument here of a to the x. And this is clearly true, so that's why we know that if your base is the same as your argument raised to some power, that log is going to be equal to just the power. Okay? A little shortcut of that sometimes people do is they say, oh, just pull that exponent down front. And then you would have x times log base a of a, and we already mentioned that when your base and argument are the same, that whole thing is 1. So this really just leaves you with x times 1 or just x. So it's another way to think about it. We're actually going to look more at that property in a minute. Okay? And then this one right here, this last one, is actually an exponential. I know it says log, but it's an exponential. We have some a base raised to some power. So if you converted it to a log, you would have log base a, base of the exponents, the base of the log, of x equals the exponent, log base a of x. And this is clearly true. So notice that if you have an exponential where the exponent is a log with the same base as what your base of the exponent was, then whatever that argument is what it's going to simplify to be. Okay? This doesn't come up a ton, but it's just good to be aware of. Okay? All right, there are 3 more properties that we're going to talk about in 4.4. Okay? First one is called the product property. The product property tells us that if you have 2 pieces being multiplied together in the argument position, so notice that this x and y are in the argument position and they are being multiplied together. We can split this log apart into 2 separate logs that are being added together. So in other words, I could take log base b of x, the first part of the argument, and log base b of y, the second part of the argument, and I could add those log expressions together. And if I did that, that would be equivalent to the original log I started with where there was multiplication in the argument position. And you go, well, who cares? Why would we ever need that? It's nice to be aware that you can go back and forth between these 2. So if you have 1 log where there's a multiplication in the argument, you could rewrite it as 2 separate logs being added together. Or if you had 2 separate logs being added together where they had the same base, you could rewrite it as a single log where the arguments were being multiplied. Okay? And that can help us depending on what numbers we're dealing with. Okay? Let me prove to you first of all that that's true. Let's say that I had log base 2 of 4 times 8. Okay? According to this property here, I could split that apart to log base 2 of 4 plus log base 2 of 8. Okay? Well, log base 2 of 4 is the number 2. Reason being, 2 to the something has to equal 4. Oh, it's 2, so log base 4 of 2 is 2. Okay, it is that number 2. If you've forgotten how to do that, if you're using a TI-84, if you hit the math button and arrow down to log base, you could type in log base 2 of 4, and it would say, oh, that's 2. Plus log base 2 of 8. Log base 2 of 8 is a number. 2 to the something has to equal 8. Oh, that's 3. 2 to the third is 8. So log base 2 of 8 is the number 3. And when I add those together, 2 plus 3, I get 5. So log base 2 of 4 times 8 should equal 5. If I type that in my calculator, log base 2 of 4 times 8, my calculator will say 5. Now, another way to think about it is, what if instead of leaving it as 4 times 8, we worked out 4 times 8 and said, oh, 4 times 8, that's 32. Okay, well, log base 2 of 32 is also the number 5, because 2 to the something has to be equal to 32. 2 times 2 is 4, times a third 2 is 8, times a fourth 2 is 16, times a fifth 2 is 32. So 2 to the fifth power is 32. So notice if I hit log, oops, I meant to do log base 2 of 32, that's also 5. And it should be, because 4 times 8 was 32. But sometimes it's harder for us to work these bigger log values in our head. We may not know 2 to the fifth is 32. Just because that's a high power, we may not have that one memorized. But if we split it apart to log base 2 of 4 and log base 2 of 8, those are logs that we probably could do in our head. And so it's nice to know that that property is there. Okay. Another property that we use quite a bit is called the quotient property. Now, think about why this is going to be true. The product property said that if you had items being multiplied together in your argument, you could split it apart into 2 logs that were being added. Similarly, the quotient property says that if you have 2 items being divided in your argument, you could split it apart into 2 logs that were being subtracted. So hopefully you kind of see that connection there. Let me prove to you that that one is true. Let's say I had log base 2 of, I don't know, 16 over 4. Okay. Well, I could split that up. I could call it log base 2 of 16 minus log base 2 of 4. Well, log base 2 of 16, 2 to the something has to equal 16, that's 4. And log base 2 of 4, 2 to the something has to be 4, that's 2. So when we work that out, 4 minus 2, we get 2. So if I type this in my calculator, log base 2, so I'm going to go to math, arrow down to log base 2 of 16 divided by 4, it's going to say 2. But if I had worked them individually, log base 2 of 16 minus the log base 2 of 4, it comes out the same, because log base 2 of 16 is 4 and log base 2 of 4 is 2. When you subtract them, you get 2. So they are the same thing. And again, it's nice to be aware of that, because, you know, if you didn't know, or let me back up for a second. Log base 2 of 16 over 4, I could have just done the division. I could have said, oh, well, 16 divided by 4 is 4, and just done log base 2 of 4. Oh, that's 2. So here's a case where I think the division was probably faster, because you would have been just working log base 2 of 4, was probably faster than working them separately and subtracting. But the answer does come out the same. So depending on what you've been given, sometimes it's nice to work it as a single log. Sometimes it's nice to split it apart into 2 logs and work them separately. Just depends on the numbers and the values that you're given. And then the third property that we need to look at in this section is called the power property. Okay? The power property has powers in it, exponents. And it says that if log base b of x to the p is your given log, then what you can do is you can pull that exponent p down front. Move that p down front and have p times log base b of x. Okay? Let me show you that that is true. let's say that I had log base 2 of 4 to the third power. Okay? Now, I could work this out. I could say, well, 4 to the third power, 4 to the third is 64. So I could call that log base 2 of 64, because 4 to the third is 64. And then I could go, okay, well, 2 to the something has to be 64. I wonder what that is. Well, 2 times 2 is 4, times a third 2 is 8, times a fourth 2 is 16, times a fifth 2 is 32, times a sixth 2 is 64. Oh, 2 to the sixth is 64, so this whole thing must be 6. Great. But sometimes people have a hard time working with logs that have big numbers like 64, okay? So another option, if you're using this log property right here, is to say, you know what, I don't like that 3 up there. I'm going to pull that 3 down. I'm going to pull that 3 down and call it 3 times log base 2 of 4. And if I do that, then my 3 is just here chilling, and I've got log base 2 of 4. Well, log base 2 of 4 is just 2. We've done that several times now. And 3 times 2 is 6. So in this particular case, I think it's faster and easier to pull that exponent down front and work the smaller log than it is to work with a log of 64. So we just need to be aware that those 3 properties exist. There's times when you're going to want to work it with a single log. There's times you may want to work it as 2 logs added or subtracted together. There's times you may want to leave an exponent there. There's times you may want to pull that exponent down front. Or the reverse of this. Let's say that I had 4 times log base 2 of 5 or something like that. Well, log base 2 of 5 is not something I can work out, but I know that that 4 could be pulled up front. So I could call this log base 2 of 5 to the 4th. And whatever 5 to the 4th is, let's see, what is 5 to the 4th? 625? So we would have log base 2 of 625. And log base 2 of 625 is something I can type in my calculator. So it's just nice that you could be able to go back and forth between the two. Okay? All right, so let's experiment with some of these and just kind of see, the pros and cons of the 2 different ways of writing them and some ways that we can work problems. Okay, actually, number 1 we've already talked about, right? We could call this log base 2 of 32. We absolutely could. And that would be, log base 2 of 32 is going to work out to be 5. But instead of working it with one big number, we could call it log base 2 of 4 plus log base 2 of 8. And I could work each log individually and add the results. Log base 2 of 4 is 2, because 2 to the second is 4. Log base 2 of 8 is 3, because 2 to the third is 8. And when I add them together, I get 5. Okay. Number 2 is a good example of why that product property is helpful. Okay. Log base 6 of 4, that's not going to be a whole number. If I've got to do 6 to the something and get 4, that's not going to be a whole number. Log base 6 of 4 is not a whole number that I can do in my head. But if I'm adding 2 logs together, I can write it at, and they have the same argument. They both have a base of 6. I'm sorry, they both have the same base, not the same argument. They have the same base of 6. I can call that one big log. Log base 6 of 4 times 9. Well, I know that 4 times 9 is 36. So really, this is log base 6 of 36. Well, I know that one. 6 to the something has to be 36. That's 6 squared. So this is going to work out to be 2. And so even though I couldn't do log base 6 of 4 in my head, that's not a whole number, it's not one I can work out, I was able to do it in my head when I wrote it as a single log. Okay? And of course, this is one you can check in your calculator. If you go to math, arrow down to log base 6 of 4 plus math and arrow down to log base 6 of 9, it's going to say, oh, that's 2. And here's what was happening behind the scenes. Okay? Remember, if you have an 84, you can hit that math button and arrow down to log base. If you do not have an 84, if you're using an 83, you have to do it a little differently. That's when you would have to type, for instance, like log base 6 of 36. If you don't have the log base 6 of 36, if you don't have an 84 calculator, you would have to type log 36 divided by log 6, and it will work for you. And we'll discover at the end of this section why that works. Okay. All right, third example here. Again, they're adding two logs together. So we know we can write that as a single log where the arguments are being multiplied together, x times x plus 1. Okay. Now notice there doesn't seem to be a base here. That base is implied to be 10. We don't have to write it, but we know that base is implied to be 10. And now since these arguments are being multiplied together, we can say log, implied base 10, of x squared plus x. If you multiply those arguments together, you'll get x squared plus x. One more little tip that I like to do here. I'm going to put that x squared plus x in parentheses because I want people to know that that entire x squared plus x, the whole thing in parentheses, is the argument. Without the parentheses, sometimes people think that x squared was the only argument and the x was not part of the log at all. They think it's just some random x that's being added to the log portion. So to avoid people from thinking that and for people to realize the entire x squared plus x is the argument, it's nice to put parentheses around that. Okay, number 4 here. Notice we're going to have to actually use two properties here. It is two logs being added together, so we can use our product property. But because of this 2 out in front of this log, it's also using our power property. So I'm going to recognize that I can pull this 2 up onto the x as an exponent. So I'll have log base 5 of 7 plus log base 5 of x squared. Notice that that x squared is my argument. Now I have two logs that are being added together, so I'm going to say it's log base 5 of 7x squared. Notice the 7 and the x squared are being multiplied together. Again, I'm going to put the 7x squared in parentheses to show people that it's not just log base 5 of 7. It's the entire 7x squared that's in the argument position. Number 5 and 6, we're going to use that same product property, but we're going to go backwards. Notice that this has a single log, so we can write it as multiple logs being added together. So I can say log 2, again they don't give us a base, but we know it's implied to be 10, plus log x plus log y. There are 3 separate logs that if you added them together would result in that same thing. Now, some people go, well, it looked simplified before, and then you made a big old mess out of it. I did, okay. The original was more simplified than what I ended up with here, but they just wanted us to make sure that we could show that these two are equivalent. So there are times where it's nice to spread them out. There are times it's nice to condense them down into a single log. We just need to be aware that both things work, okay? Similar on number 6, they look almost identical, except notice instead of an implied base 10, there's a written out base 2. So log base 2 of 2 plus log base 2 of x plus log base 2 of y. And we're tempted to call that one good and be like, oh, we're done. Okay. However, notice that the base and the argument in this first log are the same. And when your base and your argument are the same, the whole thing was equal to 1. Remember that? That was one of our properties. So I can replace this log base 2 of 2 with just the number 1 and have 1 plus log base 2 of x plus log base 2 of y. And I realize at this point you're like, who cares? Why are we doing this? It will come together later. As you move further into logs, you see more why it matters. So for now, just realize, hey, this is a true statement. I could separate this single log into 3 identical logs, and when your base and argument are the same, that whole log was equal to just 1. Okay, number 7 here. This is an argument that's being multiplied together. 3 and a plus b are being multiplied together. So we can separate that into ln of 3 plus ln of a plus b. Okay. A couple things on that. One, notice that ln is a log. Okay, this is a log even though it says ln. It's implied to have a base of e. We don't have to write the base of e. It's implied by the fact that we use ln. Okay. Also, I do need those parentheses around the a plus b. If I didn't put parentheses around a plus b, it would look like it was just ln of a. And a was the only part of the argument, and we have a random b just being added on. So we do need the parentheses around a plus b to show that that entire portion is the argument. Okay. All right, next group here. These are using the quotient property of logarithms, okay? So again, sometimes we can take a single log and separate it into two parts. Sometimes we can take two separate logs and combine them into one. The quotient property works both ways. So I can split this up to log base 2 of 64 minus log base 2 of 16. Log base 2 of 64. 2 to the something has to equal 64, and 2 to the 6th power is 64. If you're not sure, you could check. 2 to the 6th power is 64. So I know this part right here is 6. Minus log base 2 of 16. 2 to the 4th power is 16. So I know that portion right here is a 4, and 6 minus 4 is 2. So in my calculator, if I typed log base 2 of 64 over 16, it would say 2. Now, keep in mind, 64 divided by 16 is just 4. So really, 64 divided by 16 is 4. It might have been faster to say, hey, 2 to the something is 4, oh, 2. It might have been faster to do the division instead of separating it into two separate logs. But either way, the answer is going to come out to be 2. So we've kind of proven that that log property is true. At least we've proven it by example. Okay. So just be aware that sometimes it's faster to separate it into two. Sometimes it's faster to do the division. But they are both saying the same thing. Here's a case where, let's see, log base 6 of 108 is not going to be a whole number. 6 to the something has to equal 108. It's not going to be a whole number. Okay. In fact, if you typed log base 6 of 108 in your calculator, you're going to get a terrible, horrible decimal. So I can't work out log base 6 of 108. But I notice that these two logs are being subtracted. And if two logs with the same base are being subtracted, I can rewrite it as a single log. I can call it log base 6 of 108 divided by 3. I can write it as a single log. Well, who cares? Well, because now 108 divided by 3 is 36. So this is really log base 6 of 36. And log base 6 of 36, that's one I know. I know that 6 squared is 36, so the whole thing is just a 2. So in my original, this original two logs being subtracted together works out to be just plain old 2. Log base 6 of 108 minus log base 6 of 3, and the calculator tells me 2 because this is what it's doing behind the scenes. It knows those log properties. Okay. Okay. If we have two logs that are being subtracted, I know it says ln, but remember ln means log. Two logs that are being subtracted, we can write it as a single log. We can say ln of x divided by x minus 5. You will probably want to put that x over x minus 5 in parentheses to show that that whole thing is in the argument position. Here's a case where we have a single log, but we can separate it into two. We can call it log base 7 of z minus log base 7 of 49. Okay, and you go, well, why would we want to do that? Because sometimes, like in this case right here, log base 7 of 49, that's something we can work out. We know that 7 squared gives us 49, so this last log portion right here is the number 2. Now, I can't simplify log base 7 of z because I don't know what z is, but I do know that this right here and that right there are equivalent. Okay? These two expressions are equivalent, and this one's a little bit nicer because we were able to work out part of the log. Similar idea here. We can call this log base 7 of a minus log base 7 of 14. And we are very tempted to say, oh, log base 7 of 14, that's 2. 7 times 2 is 14. But remember, it's not 7 times 2 equals 14. It's got to be 7 to the whatever exponent that equals 14. So that's not going to be a whole number. If you typed log base 7 of 14 in your calculator, it's not going to be a nice, pretty whole number. It's going to be an ugly decimal. So when they don't simplify to be nice, pretty whole numbers, we don't usually simplify it. We just leave it like this. Okay? But that is, using that quotient property with logs to rewrite what they gave us. Okay? And then similarly here, we could call this log. They don't give us a base. It's implied to be 10, so I don't need to write the 10, but I know it's there. Log 100 minus log x plus y. Now, x plus y needs to be in parentheses because that whole thing is my argument. And we're tempted to say, okay, we're done. That's the best we can do. But remember, log 100 is a number. There's an implied base 10. So 10 to the something is supposed to equal our argument of 100. Oh, that's a 2. So log 100 is the number 2. Okay? So this is really 2 minus log of x plus y. And again, you do want your x plus y in parentheses to show that that whole thing is your argument. Next little group here, they want us to apply the power property of logarithms. Remember, powers are exponents. So what I can do is I can pull that exponent down front. I can say 3 times log base 2 of 2. And here's a case, log base 2 of 2, where the base and the argument are the same. When your base and argument are the same, that whole thing is worth 1. So our 3 is still there, times 1, because your base and argument are the same here. 3 times 1 is just 3. And you could check that one in a calculator. If you go to math, log base 2 of 2 to the third, it will tell you that that's worth 3. And it was using that power property. Okay. Again, I can pull this 7 down front. 7 times log base 5 of 3. Now, log base 5 of 3 is not a nice, neat, pretty whole number. 5 to the something has to give us 3. That's not going to be a whole number. So there's not really any more work we can do there. If we were to type it in a calculator, it would be a terrible, horrible, ugly decimal. So I'm just going to leave it like this. But be aware that this is a number. It's just that it's an ugly decimal. It's not a nice whole number. Okay? Power property here. Notice there's not an exponent on this 4, but there's a coefficient out in front of log. So the power property just works the other way. This 2 can come up and be an exponent on that 4 and give us log base 7 of 4 squared. 4 squared is 16, so this is log base 7 of 16. Keep in mind, log base 7 of 16 is a number, okay? It's a number. It's just an ugly number, okay? Because 7 to the something has to be 16. It's not going to be a pretty whole number. It's going to be an ugly decimal. But it is a number, okay? Notice the x to the 5th, that entire thing is our argument. But it is an argument, and that 5 that's an exponent can come out front. So 5 ln of x. If I knew what x was, I might be able to work this out further, but I don't know what x is. Okay? Number 18, same idea. I can pull that 5 out front, 5 ln e. And this is an interesting one. Remember how we said that when your argument and your base are the same thing, the whole thing was 1, like log base a of a is 1? Well, remember, when we write ln, the base is e. So this really means log base e of e. The argument and the base are the same thing, so the whole thing is 1. So ln of e is the number 1. We don't always think of it that way, but it is the number 1. So really this is 5 times 1, which is just 5. And that one's kind of cool. If you hit the ln button on your calculator, remember ln is next to the 4. ln of e, to get to the e, you type second ln. So ln of e to the 5th, and your calculator is going to say, oh yeah, that's 5. Okay. And then here's one with a radical. We kind of panic for a second. We go, oh no, it's a radical. But remember, if you have a radical with an index number, this really is just a way of writing a fraction exponent. Our x is being raised to the 2/3 power. Remember, the numerator of our exponent was what our original exponent was, and the denominator was the index number in the crack of the radical. So this is really saying log of x to the 2/3. That 2/3 is our exponent. It can come down front. So we have 2/3 of log x. Okay? And we don't know what x is. It's some variable, so that one's not a nice, neat number, or even an ugly number for that matter that we could type in our calculator, but this is the best that we can do. Okay? Now, notice some of these problems we simplified down. We got, nice, neat, pretty whole number answers. Some of them ended up kind of making a bigger mess than maybe what we started with. And that's okay. We are just trying to see how the properties relate to each other. In the next group, on the next video, they will specifically tell you whether they want you to take a single log and expand it out, or whether they want you to take an expanded log like this one and maybe condense it down to a single log, because there are times that you'll need to do it both ways.